Lecture 8 begins. Lecture 8 deals with the continuity equation and the inertial term of single-phase Navier-Stokes equation. Navier-Stokes equation is not completed without the stress term. The stress term is described in Lecture 9. Approach or method of fluid mechanics can be classified into empirical and theoretical approaches. Both have a long history and a vast amount of knowledge. The empirical approach can be called inductive theory, and theoretical approach can be called deductive theory. In this slide, I will show some of the characteristics of empirical and theoretical approaches. First, empirical approach. This approach derived formula empirical based on experimental facts. It expresses formulas such as drag force, pressure drop, etc., using empirical coefficients. The viewpoint is microscopic. The required mathematics is rudimentary calculus, and the motion can be expressed by ordinary differential equations. Treatment of phenomena is one-dimensional. Industrial problems are very complicated, so many industrial problems inevitably relied on the empirical approach. On the other hand, in theoretical approach, equations are developed starting from unquestionable principles such as conservation law. The viewpoint is microscopic. Phenomena are described using partial differential equations. Traditional fluid mechanics formed a wonderful world of applied mathematics, but I don't speak much about it in this lecture. Numerical analysis based on the theoretical approach have remarkably evolved with the development of computers. And in recent years, the application of numerical analysis to practical problems has expanded in many industrial fields. The following 6 lectures from lecture 8 to the final lecture 13 will be based on theoretical approach and focus on the analytical theory. A lot of mathematics expression and formulas will come out. Therefore, it's advisable for those who have some difficulty in understanding the structure to listen to the video repeatedly. First, let's review high school physics. Recall the Newton's motion theorem for rigid body motion. The Newton's law says that the product of the force and the time length that act on the object is equal to the difference in momentum between the two moments of time. The Newton's law is given by equation 1.1. The product of the force and the time length is called the impulse. The momentum is the product of mass and velocity. Suppose that the mass of the rigid body does not change and that the time difference between T1 and T2 is sufficiently small. The velocity difference V1 minus V2 divided by the time difference T1 minus T2 becomes the acceleration. Then the famous formula of F equal m alpha is obtained from the equation 1.1. This expression 1.2 in the yellow frame is known as Newton's law in general, but equation 1.1 is more applicable than F equal m alpha because equation 1-1 can be applied to the case where the mass changes during the motion. For example, in the case of a rocket that flies burning fuel, the mass changes during the motion. First, assume that the mass does not change. The equation of motion of a body in three-dimensional space can be expressed by equation 1-3. This equation is a second-order ordinary differential equation. Large Fx, Fy, and Fz is external forces acting on the body. In order to solve equation 1-3, initial condition must be given. Equation 1-4 and 1-5 are initial position and velocity respectively. The velocity of the body is obtained by integrating equation 1-3 with the initial condition 1-5. Further integration with the initial condition equation 1-4 give the position of the body. The equation of motion described here can be applied without any problem if the body shape does not change during the motion, like a storm. But the motion of the fluid is not so simple because the fluid is partially deformed during the motion, and deformation involves force. This problem is not lectured in the high school physics. The theme of lecture 8 and 9 is how to formulate the equation of motion of a deformable medium such as a fluid. Before explaining the equation of fluid motion, I will speak about steady and unsteady fluid motion. If you understand these words literally, time-independent motion is steady and time-dependent motion is unsteady. In the case of fluid mechanics, such a simple understanding can lead to mistakes. For example, some people misunderstand that there is no acceleration in the steady flow. The correct understanding is that in steady flow, the velocity at a fixed point does not change over time. In unsteady flow, the velocity at a fixed point changes over time. If you trace a small fluid element, you can see that the velocity of the small fluid element changes over time, even in the steady flow. The figure in the slide shows that fluid element that passes through a particular point moves to another point at the next time, and that element will have the different velocity from the previous time. Note that the equation of fluid motion is derived for the same fluid element. I will show a flow visualization photo showing how a fluid element deforms in the flow, where the flow path is narrowed in the direction of flow. Fluid elements are marked in a special visualization technique. From this photo, you realize the difference between motion of fluid and motion of breathed body. There are two methods for expressing the motion of fluid. The one is Lagrangian method and the other is Eulerian method. The Lagrangian method treats the motion of a fluid in the same way as the point mass or rigid body. That is, motion of fluid expressed as a function of time. Fluid elements are invisible and thus that method is not convenient as the method to recognize fluid motion. Fluid motion and fluid properties are usually recognized as a function of space. In unsteady Eulerian unsteady flow, time is added as an independent variable in addition to the space coordinate. The Eulerian method is to describe fluid motion as a function of the time and space coordinates. The Eulerian method is common in fluid mechanics. It is easier for Eulerian method to take into account the deformation. Deformation itself occurred regardless of viscous fluid or inviscid fluid. In the case of viscous fluid, the viscous force is expressed by deformation, and it is included in the equation of motion. There are two types of deformation: shear deformation and swell or shrink deformation. For incompressible fluid, only shear deformation occurred. The formulation of deformation will be described in detail in the lecture 9. Lecture 8 derived the continuity equation and the acceleration term in the Newtonian law, F equal m alpha. In other words, the part of m alpha is explained in lecture 8, and the part of force F is explained in lecture 9. The symbol G represents a physical quantity such as velocity or temperature of a fluid element. G is given as a function of space and time. So G is G, X, Y, Z, T. Assume that the fluid element moves at a velocity of U, V, W. G of the same fluid element after delta T can be given as G equal G X plus U delta T, Y plus G, V delta T, Z plus delta W delta T, T plus delta T. Let's define dG dt as a change in G of the same fluid element over time delta T. dG dt is given by the expression in the yellow frame. Note that the difference between dG dt and round G round T. Round G round T is the change of G at a fixed point. dG dt is the change of G of the same element which moves from point to point. If G is velocity, acceleration expressed by dG dt, not round G round T. Using the Taylor's expansion of series for G lead to the expression in the red frame on the fourth line. Even if you hear the word Taylor expansion series for the first time, I hope that you will be able to understand this expression. Substituting this into the formula in the yellow frame, dG dt can be expressed in the second yellow frame. The dG dt expressed by this equation is called the substantial derivative. The first term on the right-hand side is called local differentiation, and subsequent terms are called convective differentiation. When G represents fluid velocity u v w, dg dt becomes the acceleration term alpha in Newton's law. In order to derive the equation of fluid motion by the Newton's law, the law should be applied to the same fluid element. Thus, the acceleration of fluid must be given by dg dt. The equation of motion is derived from the Newton's law that mass times acceleration is equal to the force. Acceleration terms can be obtained by applying g to the velocity u v w. The acceleration terms in x, y, z direction are shown. If the force is given, the equation of motion is completed. When the force is related to the deformation of the fluid element, it is appropriate to consider the small fluid element in space as shown in the figure. And the force due to deformation is formulated using this fluid element. Also, the equation of motion can be derived by formulating the mass and the momentum that goes in and out of this small element. The energy equation can also be derived by considering the thermal energy that goes in and out of the small element. This small element is called control volume, or it is sometimes called shortly CV. From here, I try to derive the equation of motion using the control volume. In the following, the problem will be treated two-dimensionally for simplicity. In the world we live, all the physical phenomena, solid or fluid, are governed by three laws of conservation. That is, conservation laws of mass, momentum, and energy. Shape, velocity, temperature of object can change, but the total mass, total momentum, total energy are not generated nor extinguished. Below, we only consider the conservation of mass and momentum. First, the figure for deriving the equation of conservation of mass is shown. The product of density, velocity, and cross-section is the flow rate per unit time. The thickness of the sky blue control volume is 1. So the line segment delta x, delta y means not only the distance, but also the cross-sectional areas. When the inflow from the OC surface is rho u, the outflow from the AB surface is rho u plus round rho u round x times delta x. Similarly, when the fluid rho v enter from the OA surface and exist from the BC surface, the outflow from the BC surface is rho v plus round rho v round y times delta x. When considering the inflow and the outflow of mass, it is only necessary to consider from which direction the inflow and outflow into the control volume, because the density is a scalar. Since momentum is a vector, it has a directional component. Therefore, when considering the equation of momentum conservation, it's necessary to consider the inflow and outflow from each direction for each of the momentum rho u and momentum rho v. Fortunately, the matter is not so complicated. All you have to do is to replace rho for mass conservation with rho u or rho v. The figure shows the inflow and outflow of momentum from each surface. Based on the inflow and outflow of mass explained on the previous page, we will derive the equation of conservation of mass, that is the continuity equation. The difference between the mass flowing in and out of the control volume is given in the yellow frame. This difference is generally not zero. This is because the density may increase or decrease over time within the control volume. The amount of increase or decrease in mass within the control volume is expressed by the time derivative of density multiplied by the control volume. According to the law of mass conservation, the amount of increase or decrease in mass within the control volume is equal to the difference between the mass flowing in and out of the control volume, as shown in the second yellow frame. If the volume delta x, delta y on both sides is reduced, it becomes the continuity equation shown in the second yellow frame. This is the two-dimensional continuity equation. The three-dimensional continuity equation is shown in the third frame. In the previous explanation, the continuity equation was derived from the amount of fluid flowing in and out from each side of the control volume, but using Gauss divergence theorem, we can easily derive the continuity equation. The Gauss divergence theorem was explained in lecture 2. The content of the theory is that in the volume V surrounded by the closed surface S, the relationship between the volume integral and the surface integral of the arbiter vector A is given by the equation in the yellow frame. The law of mass conservation can be described in words as follows. The increase or decrease in the mass of the fluid in the volume V is equal to the mass of the fluid flowing in and out through the surface S surrounding V. That this description of mass conservation can be explained by this equation. As shown in the second yellow frame, the surface integral on the right-hand side can be replaced by the volume integral using the Gauss theorem, where rho u assigned to the vector A. Substituting the relationship of the yellow frame into the right-hand side of the above equation gives the expression in the third yellow frame. This equation has no restriction on the integral domain. So the integrand satisfied relationship shown in the right of the arrow. This equation is the equation of the continuity. If we express each component without using nabla, it will be the last formula. Based on the inflow and outflow of momentum, we will derive the equation of conservation of momentum, that is, the equation of motion. Let's start with the motion in x direction. The derivation procedure is almost the same as for the continuity equation. Just replace density law with law U. The difference between momentum rho U flowing in and out of the control volume is given in the yellow frame. The change in momentum rho U of the control volume per time is expressed by the time derivative of rho U multiplied by the control volume. This change in rho U balances the momentum flowing in and out of the control volume and the force Fx acting on the control volume. This balance gives the equation of motion. Large Fx is replaced with small Fx, which is the force per unit volume. If the equation divided by the volume, the equation of motion in x direction is obtained as shown in the last yellow frame. The equation of motion in the y direction is shown in the yellow frame. This derivation of this equation is almost the same, except that rho u in the x direction is changed to rho v. So the explanation omitted here. If you already want to see it, try it by referring to the previous slide. At this stage, I have not mentioned anything about how to express the forces acting on the fluid element. I have only shown the acceleration or inertial term. The next lecture, lecture 9, deals with the forces concretely. In the slides so far, I have written formulas for each component and used vector. From now, tensors are indispensable. Therefore, I will explain the vector and the tensor notation so that you become familiar with vectors and tensors. Vectors and tensors are used as tools to represent complex expression concisely. In research papers and technical books, equations are written often using vector and tensor without any explanation for such notation. Vector and tensor are ruled, and once you memorize them, you will find that they are very convenient. If you write the continuity equation using each direction component, it becomes equation 1 and 2. If you write the same equation using vector and tensor notation, the equation becomes concise. In the tensor notation, the Einstein summation convention is applied. The Einstein summation convention is as follows. When the index variable appears twice in a single term, it implies summation of that term over all the variables of the index. There is the episode that Einstein jokingly states that this notation was his greatest invention in mathematics. If you write equation of motion using each direction component, it becomes equation 3 and 4. If you write the same equation using vector and tensor notation, the form of the equation becomes very concise. In the above example, The tensor shows only the direction of the motion, so there is only one subscript. In the case of force, a stress tensor appears. The stress tensor is described in the lecture 9. In the case of stress tensor, two directions are related, the direction of the surface and direction of the force. If you do not use the tensor notation, expression of equation become quite complicated. We have defined substantial derivative dg dt in the front part of this lecture as shown on the first line. Substituting the velocity u to g, x component of acceleration obtained. The third line shows the equation of motion described by the tensor. The left-hand side is the inertial term or acceleration term. It will be shown below that the left-hand side of I equal 1 is consistent with the du dt on the second line. Putting ui equal u and rewriting the formula according to Einstein summation convention, we get the formula on the fourth line. Expanding the formula on the first line, give the formula on the fifth line. If we enclose the formula on the fifth line with rho and u, you get the formula on the sixth line. You can see the inside of parentheses enclosed in u is 0 owing to the continuity equation. The inside of parentheses enclosed in rho is the substantial derivative of u. As a result, you can see the left-hand side of the third line is the same as du dt of the second line. The same is true for I equal 2 and I equal 3. This is the end of lecture 8. Thank you.